Okay, so we're actually going to look at classifying chemical reactions today, and we're going to just start with looking at what a chemical reaction is and a few ways that you can tell it's happening. All right, so chemists tell between the four chemical reaction types: synthesis, combustion, decomposition, and replacement reactions. So there's actually two different replacement reactions, and we're going to talk about those a little bit separate from everything else. And so by analyzing and comparing reactants and the products of chemical reactions, you can begin to notice patterns that will help you classify them. Now, some reactions fit into more than one of the types. Some evidence that you can use to tell if a chemical reaction is even happening are things like temperature change, heat and light release, absorption of heat, color change, gas bubbles, odor, and the formation of a solid. So if you mix two liquids and a solid comes out of the mix, then you've had a reaction. Okay, and we'll talk about that particular product when we talk about those double replacement reactions. So the first reaction that everybody gets exposed to is a synthesis reaction. A synthesis reaction is where two or more substances react to produce a single product. So we've used this a lot in like practicing making ions and practicing creating covalent compounds because you're just putting two things together and you're creating a compound. And so when two elements react, the reaction is always a synthesis reaction. So basically, this is when you guys have been practicing like from last quarter all the way through this quarter. And so the example here is sodium and chlorine combine to create sodium chloride or table salt. Okay, right? Sodium's a metal, chlorine's a halogen, and then it creates an edible product, table salt. Combustion reactions are where oxygen combines with the substance to release energy in the form of heat and light. Oxygen can combine in this way with many substances. So this is an example of hydrogen and oxygen combining in a combustion reaction, releasing heat and light, and it produces water. Okay. Other combustion reactions are things like burning wood. So chemically speaking, that would be the carbon compounds in the wood are combusting with the oxygen. Okay. And so for combustion to happen, you have to have oxygen. If you don't have oxygen, you don't have combustion, you don't have fire. That's why a lot of fire prevention methods smother the oxygen out of the reaction. They make it so that no more oxygen can be provided. So whenever you see firefighters using foam with their water, that's what the foam does. It smothers that reaction. A decomposition reaction is just the exact opposite of a synthesis reaction. In a decomposition reaction, you have one compound and it breaks down into two or more elements or new compounds. So with decomposition reactions, you don't necessarily get elements. You can get two compounds. So if you break apart a polyatomic ion, right? Ammonium chloride, okay? It's NH4ClO2. If you break that apart, you still have two compounds, right? We treat them as a unit because they're ions when they're separate, but those are technically compounds. Okay, so with decomposition reactions, what you're really looking for is like one thing breaking into more than one piece. Okay. All right, so now we're going to start looking at the replacement reactions. Remember, I said there's two. In a single replacement reaction, the atoms of one element replace the atoms of another element in a compound. So you can use the generic equation that they have here, but I know that a lot of you that looks familiar to a couple of generic math equations. So if that's the case for you and this is going to be confusing, you can write in A plus BC yields AC plus B, okay? You do not have to use theirs. If that works out better for you to have the C in there instead of an X, because the X confuses you and makes you think that it's a math equation, that's fine. Okay, it just represents the partner that switches places. Okay, so in the single replacement reaction, you're taking a compound and you're introducing another element, and that element is going to replace something in that compound. Okay. Most often it's the cation, but it can be the anion if it's a halogen. So we're going to look at the reactivity series now that determines how that works. So reactivity is your ability to react with another substance. An activity series, which is shown on the right of this slide, can be used to predict reactions. So if you look at the activity series, and I'm not going to read all the text because it's going to tell you the same thing. The higher you are on the list, the more likely you're going to replace something. So lithium is most likely to replace all of the other metals on this reactivity series. If you're looking at two metals and you're trying to decide if one's going to be replaced, the one doing the replacing has to be higher on this list. So if you've got nickel and you've got a copper compound, say copper sulfide, and you want to know if that nickel is going to replace that copper, you're going to come over, you're going to check your activity series, and you're going to see that it's higher up on that activity series. That means nickel will replace the copper, okay? But let's say you have a magnesium compound and you've introduced zinc. Zinc is not going to replace magnesium on its own because it's lower on that reactivity series, okay? If your halogen is what's getting replaced and you have iodine, and you're introducing chlorine, absolutely, that's going to be replaced. But if you have a fluorine compound, okay, and you introduce bromine, it's not going to replace it because bromine's lower on that list, okay? So it has to be higher on the list to replace whatever is in the compound. Okay. Double replacement reactions are when both compounds switch partners, okay, whether it be the two halogens switch or the two metals switch, okay? And so they represent this with AX plus BY yields AY plus BX. Again, if the X and Y is confusing for you, feel free to replace those with any letter as long as you're consistent, okay? And so the example they give here is calcium hydroxide plus hydrochloric acid gives you calcium chloride and water, okay? So if you look at the example, you have an OH here for your hydroxide, and that OH pairs up with the H from the HCl to give you H2O, okay? So that has switched partners from the A partner to the B partner, and the chlorine has switched from the B partner to the A partner. Double replacement reactions always occur in solution, and they only produce one of three things: a water, a precipitate, which is that solid from a liquid that I was talking about, or a gas. So when you combine two things, if a double replacement reaction happens, you're going to see water, you're going to see a solid form, or you're going to see gas bubbles. Okay? The water is hard to tell if you're looking at something already in solution, which is the only way that double replacement reactions happen. But you can determine that by things like checking pH before and after the reaction and things like that. Precipitate, super obvious. Gas is pretty obvious too. The bubbles aren't usually super subtle. It's usually like looking at a soda almost for most of the double replacement reactions. And that's really it on the types of reactions. So using those generic equations of, A plus B equals AB for synthesis, A plus O2 gives you AO plus heat, energy, light, water, whatever that product is of the combustion. A decomposition reaction is AB yields, A plus B, and then the two replacement reactions. And again, in the guided notes, there's not AX because I've had students in the past tell me, this reminds me of math and it's not a math equation and I want to solve it like a math equation, so can we use another letter? In yours, it's D's, C's, D's, A's, and B's, okay? So you can use either form of that generic equation. As long as you're consistent with where you put the letters, it doesn't really matter what you use to represent them because they're just there as placeholders for chemical. All right, I'll see you guys in the next video.